So in reaction mechanism 20, we're going to reverse what we saw in reaction mechanism 19, where we were hydrolyzing esters, and now we're going to make them. So again, we're going to see a lot of hydrolysis chemistry when we understand how enzymes work. And this is, again, just a reversal of that hydrolysis chemistry. So where hydrolysis chemistry involves using water to break these linkage bonds, now when we make these linkage bonds, we're going to generate water. So again, that's a commonplace thing that we'll see when we have chemistry that links or condenses these small units together. So again, reaction mechanism 19, and there was other hydrolysis reactions that we had. Water is going to be at that necessary reagent. And again, we're going to be now generating water as we do this condensation chemistry. In organic chemistry, you learned this as Fischer esterification, and generally this proceeds via an acid catalyzed mechanism. So let's go ahead and draw out this mechanism. So we're going to have carboxylic acids. We're going to need to protonate this carboxylic acid to make it a better electrophile, to better react with our nucleophilic alcohol, which again, alcohols aren't great nucleophiles. So again, our protonated carboxylic acid is much more susceptible to nucleophilic attack by our weaker alcohol nucleophile. Commonplace chemistry that we see here is we have to deprotonate what was our incoming nucleophile, and we're going to protonate what we'd like to be a good leaving group. So deprotonation of what was our incoming nucleophile, and then protonation of what we want to be a good leaving group. So again, to highlight, we could put this deprotonation step simultaneous with this nucleophilic attack, so that would be totally appropriate to show the base sort of abstracting this proton and using those bonded electrons to do the nucleophilic attack. Kind of totally fine to show those together. And again, we're going to show these two kind of protonation and deprotonation events because we need to make sure that this is not a good leaving group and this guy is, in order to move our chemistry forward. So getting now we've got water as a good leaving group. Our alcohol is no longer a good leaving group. We are going to have that leaving group depart. This again is a common theme that we see. Our leaving group departs because we have adjacent heteroatom who has a lone pair of electrons that it can donate to reform our carbonyl containing compound, with the departure of our leaving group there. And now we're going to generate our protonated ester here. Pretty straightforward reaction to now deprotonate and generate our final product. And one of the things just to kind of highlight that's parallel to what we saw with our acid catalyzed hydrolysis is we do regenerate our acid that we started with, confirming that this is an acid catalyzed process. So again, not too much to comment. There's really not anything to highlight on that I haven't already highlighted in previous mechanisms. A lot of things that we've sort of talked about have come into play here. Not too much more to say. We only have 3 reaction mechanisms left to go. So just a couple of comments on sort of the application here. So kind of where are we going to see this chemistry? We're not necessarily going to see a ton of ester-containing biochemical or biological functional groups. But one that we will see is in our triglycerides. So triacylglycerols or triglycerides, TAGs is what we'll abbreviate them for short. Again, we've seen these where we kind of have an upside down W that I'll draw with or hold with my hands. Kind of that's like our little symbol for triglycerides, where the 3 fingers that I'll dangle down represent the 3 fatty acid moieties. My 3 knuckles represent the 3 carbon atoms of that glycerol backbone. So again, the chemistry that occurs between the 3 hydroxyl groups on glycerol and the carboxylic acids on those 3 fatty acids are what we use to generate these triglycerides. And again, triglycerides are nature's favorite mechanism for storing energy. Storing energy is those fat molecules that are worth so much more, 9 calories per gram versus the 4 calories per gram that we see for carbohydrates. So again, toggling between this chemistry and that of, we should say, reaction mechanism 19 here, the one that we just had to disconnect those fatty acids, is also an important process that allows us to have these fats be taken up in our intestinal tract, right? So in our intestinal tract, these are triglycerides that are hooked together with that ester linkage. We need to disassemble them into our fatty acid components because that is what we're going to be able to absorb in our intestinal tract. So again, if you cannot disassemble a fat into its component fatty acids, you're not going to be able to absorb them from dietary sources. So again, thinking about this in terms of a context of a fat substitute, like something like Olestra. So I'll blow in and show this structure in a minute. Olestra was kind of touted for a long time as a really great fat-free fat substitute. So again, it has structural similarity to natural fats. We're going to have fatty acids that we basically esterify to a hydroxyl group. But rather than it being on the 3-carbon glycerol backbone to make the natural triglycerides, we're going to use sucrose. We're going to use a sugar molecule, and we're going to basically decorate it. So I'll blow up on this. Actually, let's do it right now so we can see it. Here is sort of the structure of Olestra, and we're going to have this sugar molecule, and remember, sugars very prevalent hydroxyl groups. So all of the hydroxyl groups are chemically esterified with saturated fatty acids here. So it makes kind of a synthetic fat that has the mouthfeel of a natural fat. But again, we do not have the enzymes that will recognize this as a substrate. So we do not snip these off. So these fatty acids do not leave the intestinal tract and go into your bloodstream as a fuel. So this whole thing remains intact in your gastrointestinal tract. So again, the inability to break these linkages renders this molecule basically inaccessible from a dietary fuel standpoint. So again, this is going to be something that's calorie-free because we're not able to take it up into our body. Other things that might be calorie-free, and we'll talk about this with artificial sweeteners in our carbohydrates unit, if we cannot break down things in the body, as is the case that we see with sucralose or Splenda, or maybe we have such small amounts that it's basically calorie-free, like we see with NutraSweet or aspartame. This is where a lot of these synthetic sort of diet supplements have come from. Is they're either not able to be actually taken up into the body, not broken down by the body, or present in such small amounts that we can basically label them as calorie-free. So we're going to take a deeper dive into that in our learning unit on carbohydrates. But again, wrapping up here with thinking about the formation of ester linkages in lipids.